Hello, and thanks for joining the webinar today. We're going to give folks another moment to log on and we'll be starting soon. Okay, let's go ahead and get started. Welcome to our first Better Climate Challenge Technical Assistance webinar. These webinars are a chance to dive deeper into decarbonization topics and technologies. Today's webinar is called Using Heat Pumps to Electrify Existing Buildings, and we'll be presenting case studies from the field. Please note today's webinar will be recorded and archived on the Better Building Solutions Center. We will follow up when today's recording and slides are available. And next, I'd like to let attendees know that you are in listen-only mode, meaning your microphones are muted. If you experience any audio or visual issues throughout the webinar, send a message to the Q&A box located on the bottom of your Zoom panel. So we are very excited about this webinar because heat pumps have been a very popular topic for the Better Climate Challenge partners. And I'm sure this is also a topic of interest to other Better Building partners on the line. Next slide. So now I'm going to introduce today's speakers. My name is Nora Hart. I'll be your moderator today. I work for Lawrence Berkeley National Lab, and I provide support to the Better Climate Challenge. And fun fact, this is my first time hosting a webinar, so we'll see how this goes, and hopefully I get invited back. And I am joined today by an amazing lineup of presenters. All of the presenters that you see here on this slide are technical account managers for the Better Climate Challenge. So first we have Alper. He is a technical account manager, or TAM, as we call them for short. He's an LB&L affiliate and he works for PAE. For the Better Climate Challenge, he works with our multifamily partners. Next, we have Dan Luddy. He's also an LB&L affiliate who works for PAE, and he is working with our state and local government partners on the Better Climate Challenge. And finally, we have Stet, who you may have seen before. He's done a lot of these webinars, and he is also an affiliate. He works for Smith Group, and he works with our Better Climate Challenge partners. Next slide. So this is just a short meeting agenda to let you know we will be doing a Slido poll to kick things off. I'll have a couple of slides on heat pump fundamentals, and the bulk of the time will be spent on the 4 heat pump case studies. Next slide. Okay, so today we will be using an interactive platform from Q&A for polling. So please go to www.slido.com on your mobile device or by opening a new window in your internet browser. And today's event code is DOE. If you would like to ask our presenters questions, please submit them anytime throughout the presentation, but we will be saving all of them for the end. And you can select a thumbs up icon for questions that you like. So those will result in being the most popular questions moving to the top of the queue, and we'll answer those first. Okay, so please join us over at Slido to respond to the following questions. If you're having any issues, message our tech support team by using the Zoom Q&A function. So this first question is, what barriers did you encounter or are you currently facing on your heat pump projects? And we'd like you to select all that apply. So there are a couple of things we have listed out here that may be potential barriers: cold climate operation, cost of electricity, electrical service constraints, difficulty communicating benefits to leadership, heat pump footprint, or maybe you're just unclear on heat pump options and you want to learn more. So it looks like a lot of these are getting similar responses. We're kind of jumping around a little bit between what's the top selected response, but it looks like a lot of these are barriers for everyone on this call. So I'll give it just a couple more seconds to see if something jumps to the top. Okay, it's looking like upfront cost is the biggest barrier. And just so you know, we're kind of using these polls to better understand our audience, but also to help us build out resources in the future. So with that, let's move to the next poll. Okay, so this one's more simplified, but we just want to know, what heat pump technology are you most interested in learning more about? air source heat pumps, water source heat pumps, variable refrigerant flow systems, or ground source heat pumps. And again, we'll use these responses to help us develop potential case studies in the future or things that we know you want us to focus on in future webinars. So it looks like for this poll, air source heat pump is winning out, which is great because some of the case studies that you'll see later focus on this type of heat pump. Okay, great. With that, I think we will jump back to the slides. Thank you all for participating in Slido. And as a reminder, you can enter your questions in Slido throughout the presentation. So now I'm just going to give a brief overview on heat pump fundamentals to kick us off. So heat pumps are key to the electrification of HVAC. And here I'm giving a simplified visual on the difference between a boiler versus a heat pump for heating. And what I want to highlight here is the fact that boilers create heat, whereas heat pumps are just moving heat. Heat pumps are transferring heat from a source, in this case, the outside air, into the building to warm the space. So for this visual, we're showing the heat coming from the outside air, but it could also be the water or the ground in different heat pump types. And heat pumps can also be used for cooling. So in that case, the process would be reversed. We can go to the next slide. So why heat pumps? Why are we so focused on this for electrification? Mainly because heat pumps are highly efficient. So natural gas combustion converts one type of energy into another type, which results in some losses and has a max efficiency of 96%. So heat pumps, they're not converting from one form of energy into another. They're instead, as I said before, moving heat from one place to another using the refrigeration cycle. This makes them a lot more efficient, and they can be up to 500% efficient compared to boilers. So this means for every 1 unit of electricity used, it can create 4 or 5 units of heat. Now, while they may be slightly less efficient in cold temperatures, heat pumps can still operate below freezing without backup heat. And finally, when combined with on-site solar PV, they can result in significant greenhouse gas reductions, even a region with a dirty grid. Next slide. Okay, so this slide is introducing the 4 case studies that you'll see from our presenters. So we chose these case studies for a couple of reasons. They're all retrofits. So we want to show that it is possible to retrofit an existing building with heat pumps. They cover a wide range of commercial buildings and existing systems. They cover a wide range of heat pump types. And finally, our speakers were involved with these projects, so they have lots of great details and can answer your questions. So the first case study you'll be hearing about is an art museum transformed into an all-electric co-working lab. Then we'll be talking about a 6-story mixed-use commercial building renovation. The third case study will be a boiler to heat pump in a historic landmark. And the 4th case study will be a net positive energy all-electric retrofit. And I want to send a reminder to you guys about these Slido questions. At the very end, we will show this case study slide again to help you remember which case study you may have a question about. So with that, we can go to the next slide, and I'll pass it over to Alper to talk about the first case study.
Thank you, Nora. Hi, everyone. So yeah, today's first case study is UC Berkeley's Baker Bioengineering Hub, which is located in Berkeley, California. And we picked this one to show that even, an existing building with challenging architecture and a challenging new program can be successfully electrified with heat pumps. Next slide, please. So the project is a major renovation and consists of conversion of a brutalist style modern art museum into a life science startup incubator building. And the building has labs and office spaces to support these new life science startup companies. The new program includes around 20,000 square feet of molecular biology labs, 20,000 square feet of office space, and also support spaces, other support spaces totaling up to 90,000 square feet of total building area. And the construction for a new building began around 2019, and it had its grand opening earlier this year in 2022. Next slide. So the existing building is, as I mentioned, is a modern style concrete building. The majority of the envelope consisted of exposed concrete walls with little glazing on the vertical envelope, and it has single pane skylights in the atrium area, which you can see on the image on the left, like in white areas. The area around the center is the skylights around the atrium, and then around the perimeter you also have single pane glass skylights as well. And all the concrete walls in this building were load bearing, meaning that the project team couldn't punch big holes for new ducts in the building. So that kind of drove the design decision for a new system in a certain way, which I'll get more into that. Next slide, please. So the project had various sustainability goals, but the two main targets that drove the design direction was UC Berkeley's net zero carbon emissions goal by 2020 for scopes 1 and 2. And then they also have net zero carbon, including scope 3 by the year 2050. And again, around the design timeline of this project, City of Berkeley was also coming up with its natural gas ban, which was the first in the nation where they were banning natural gas supply to new buildings. Even though there were some exceptions for existing buildings and some lab programs at that time, it still started the trend of going all electric. That drove the design of the new building systems to be all electric. And in addition to carbon emissions reduction targets, UC Berkeley again had its campus policy to have a certain EUI target, which is short for energy use intensity of the building. So we had to be around 80 kBTU per square foot per year or less, which is quite low for a building that includes lab program. Next slide. Starting the design team did a bunch of improvements on the building envelope, and these were all low-cost improvements, to help with supporting the building systems with all electric design. And this involved adding roof insulation on the roof, adding addition of R23 additional insulation layer, removing the existing single pane skylights and putting double pane insulated low E glazing. There was a small amount of windows on the vertical facade, which is hard to see from the images, but for these, instead of replacing the windows, the project team went in adding low E film as a lower cost improvement option. And then lastly, which you can see in the image as well, on the ground level, there is some new additional space and then for this space, we added insulated low E curtain wall with sorbent 90 glazing. Next slide, please. So the existing building systems were very highly integrated with the building facade, and keeping in mind that was an art museum. And here you can see in the images some equipment being on the roof in mechanical wells. You're seeing on the right an image of a cooling tower and some other equipment, but the majority of the equipment were in the basement. Next slide, please. So the equipment in the basement consists of 3 large air handling units to serve the building. It was an all-air system. And the building also used steam heat exchangers that was connected to the UC campus steam loop for space heating and domestic hot water heating. But having a steam loop in your campus doesn't really go hand in hand with the whole net zero energy and carbon goals. So our design team has chosen not to use that strategy anymore and install on-site heating system. For the cooling side, the building had an water-cooled chiller with the cooling tower, as we saw on the roof. Next slide, please. So as I was mentioning before, the building posed challenges in the sense that we couldn't really change the facade openings or any other openings in between the concrete walls. So that kind of put limits on the air capacity that you can get into the building. The existing building system included a total air intake capacity of 60,000 CFM from outside. So we were limited with this capacity since we couldn't put additional louvers and additional, risers to bring the air. To serve all the loads in the lab program and other spaces, the design team has chosen to go with hydronic cooling system approach. So in this approach, we had a dedicated outdoor air system that was looking in the roof, but coming from the outside air intake louver you can see on the image, to keeping the same 60,000 CFM capacity. And then the remaining of cooling and heating is provided with 4 pipe terminal units at each space. And these terminal units get heating hot water and chilled water from the central plant, the building central plant. They have like individual heating coils and cooling coils at each zone. And the heating hot water and cooling hot water to these systems are provided by air source heat pumps that are located in the equipment yard outside the building. And this is a modular heat recovery heat pump system that consists of around five modules. And they can provide both simultaneous heating and cooling. Next slide, please. So adding this system resulted in, we looked at the benchmarks and the average building uses. For a lab building in this area, you have a median of 220 kBtu per square foot. With the proposed design, we were able to achieve an EUI target of 78 kBtu per square foot. That's like a 35% reduction from a LEED baseline system. Next slide. And looking at a bit more detail about where these savings are coming from, and in these graphs, you can see the breakdown for each end use. Most of the savings came from heating energy through the use of heat pumps, as well as we had some fan energy savings, again, using 4 pipe terminal units. We also put LED lighting in the building. So we have some savings on the lighting as well, lighting energy. And next slide. And in terms of the carbon, comparing, if we had a new building, if we had built this building as a new building with typical chiller and boiler, like a water-cooled chiller and a gas boiler central plant, and comparing that to reusing an existing building and going all electric for that, the overall carbon emissions reductions, including, rough placeholder for an embodied carbon for the building over the 50-year building life cycle, we were able to achieve 47% of reduction, and around 27-30% of that carbon emissions reduction is coming from the energy, the building emissions, with the 20% coming from the reuse of the existing building. And next slide. And then lastly, just to sum up, again, this example is here to show us, you can achieve all electric design in older buildings, even with challenging architecture and challenging new programs, including lab use. And in terms of the cost, since that was a question, the cost of the system, roughly speaking, was about 20% more than a typical new plant using air source heat pumps. But as you have like larger building areas, what we were seeing is that that cost delta kind of goes down, and the cost of air source heat pump central plant systems kind of get closer and closer to typical new central plant equipment. And thank you, and I'll pass it on to Dan for the next case study.
Okay, thanks, Alper. You're right on time. So I think we're doing great here. Okay, I'm going to speak about one of my projects, which is called 419 Occidental, which is also its address, and it's located in Seattle, Washington. This is a 7-story core and shell building that's office spaces. It started life as a warehouse next to the Port of Seattle. It's a landmark historic building in the historic Pioneer Square district downtown. And it's got one level or a first level and basement that is retail and restaurants and sort of street level options there. And then levels 2 and above is all being retrofitted for future offices. And they're particularly targeting startup tech companies to come into this space. And so wanting to retrofit the building to make it more appealing there. Next slide, please. The owner is a long-term owner, held it for a while, wanted to do this major retrofit to appeal to newer tenants and to continue to hold this property for a long time. They were really sustainably minded as well, and what the sort of decisions they wanted to make. So the building itself, as I mentioned, it's landmarked, so that presents certain challenges around what we could and couldn't touch on the structure of the building. It was a full renovation of all the interior systems. So we had that opportunity to completely replace mechanical systems, electrical systems as part of that refurbishment. There was an additional stairwell added to the outside for egress. That was a little bit of sort of new construction, which we could also build to a higher standard. And as part of the sustainability targeting, the owner elected to pursue all electric heating for their systems. They were really interested in that in order to have a really efficient building overall. Partially to meet their LEED targets, this project is LEED Platinum certified, but also just from a buy and hold standpoint, they want to have a high performing building that has low operational costs for the long term. Next slide, please. This is a graphic that shows some of the key items of sort of high performance items that we included in the building and studied. As I mentioned, because it's landmarked, we were really limited in what we could see with the envelope, which is kind of counter to what the usual recommendation is when it comes to retrofitting buildings to make them electrified. Is usually the first step is get your heating and cooling loads down as low as you can, so that your new equipment coming in can be a lower capacity, lower cost for that. That means trying to refurbish the envelope as much as you can. However, we couldn't because we needed to maintain that exterior aesthetic look to the building. The windows had to be sort of like for like, looking exactly the same as they were. So we couldn't really add insulation on the outside. On the interior side, there was a desire to maintain sort of exposed brick look as well, which kind of meant that a lot of these envelope assemblies are still uninsulated. We worked with the architect to make improvements where we could, sort of at the roof level when they were replacing a new roof. Some of the windows on the storefront first level were able to be retrofit, and they were able to find good high performing solutions that also meet the aesthetic criteria. So doing what we can around the edges to try to bring down the loads. On the mechanical side, as we'll talk about in a little more detail on another slide, but the key things here was that we have dedicated outdoor air systems that deliver ventilation to all the floors. And the benefit there is that it has heat recovery on it. It provides a more efficient solution to delivering that ventilation and separates it from the heating and cooling, which means that those two systems, the ventilation and heating and cooling, can be optimized and run more efficiently as separate systems. There's also PV on the roof, and we'll talk a little bit about the roof and the footprint around there as well. And so, yeah, that's kind of where this project was ending up. So let's go to the next slide, please. This is just an image showing some of the improvements made to the first level where we could make improvements to the building itself. There was a new mezzanine that was put in that uses cross-laminated timber. So another focus of the project was to just have a relatively low embodied carbon emissions profile to the materials that were going in. And this is a good shot too of the newer storefront windows that were put in that have a higher performance than what was previously there. Next slide. When it came to the mechanical systems and discussing the idea of going with a heat pump-based system, there was some reservations around the performance of different heat pump solutions. The owner wanted to make sure that we were selecting something that has a good track record, that is reliable, and also has just met the budget. This is a market rate building, and so there was an emphasis on making sure that this came in at budget. However, we wanted the discussion to focus on other areas of the decision-making besides just the first cost. That's usually the thing that is front and center. But we like to use this sort of weighted factor chart. We call it sort of our consumer report style chart, where we work with the owner and the design team to identify the points, the metrics that make the most impact to them, whether it's first cost, whether it's aesthetics, whether it's the sort of physical constraints in the building and how much room we have for ductwork and for piping, things like that, maintenance, some of these other considerations, and go through as a team and weight what's really important, and from 5 being the most important to 1 being the least important, so that as we're making this decision as a team, we kind of understand where everyone is, and we can together kind of weigh these things, with cost being one of the components, but not the overriding component when we're looking at these systems. So this is successful in helping us as a team work out what would be the best solution. Next slide, please. One of the key constraints that turned out from this exercise was that the roof, and with easily being overridden with all the equipment, potentially with some of the different solutions. If we went down the route of having a VRF system or some of these other sort of distributed systems with a lot of outdoor condensing units, then that would add a lot of footprint mechanically to the roof space. And there's already a lot of competing interests between having amenity space for tenants, having solar PV on the roof, with some of the other existing mechanical requirements as well. And that also impacted cost too, because if the owner can have a larger amenity space that they can include, and they can charge more in rent from their tenants for this additional perk. And so there was a competing interest in terms of, can we provide a solution that's compact enough, efficient enough, and still meets the bottom line. Next slide, please. This is a quick overview summary of the proposed system. The diagram on the right is very complicated, but I will just walk through it very quickly. There is a central air to water heat pump that provides both hot water and chilled water, and that's distributed throughout the building. That is located in the basement on this diagram, but since then we ended up being able to fit it on the roof where it can live happily. It does have heat recovery, so it can simultaneously heat and cool and reuse the heat that's being rejected out of the chilled water loop and put that into the heating for the building. As I mentioned, there are dedicated outdoor air systems that provide the tempered ventilation air to all the floors. That operates separately. And then when future tenants come in, they can add their own terminal units to the hot water and chilled water loops. They can put in fan coils. They can put in more efficient options like chill beams, active chill beams, to condition their space. And I'll also point out that the owner, as sort of a belt and suspenders backup to this whole system, elected to put in gas-fired condensing boilers to back up the air to water heat pump. Those boilers are meant to run only when the system may be down for maintenance. If it's down for maintenance for an extended period of time, those boilers can turn on and provide a backup. In Seattle, it's a cold climate, but it's a relatively mild cold climate. We don't see days below 0 degrees Fahrenheit that often. So we're comfortable designing a system around a heat pump, this particular heat pump that can operate down to those temperatures that we see in a winter condition in Seattle and do so comfortably. In a colder climate, it could also be possible to use those boilers as a backup situation where they could automatically turn on and provide supplemental heating on the coldest of days if the heat pump wasn't able to meet the capacity. So there are hybrid solutions available out there too, where the heat pump is the first stage, covers most of the heating, and then on those particularly cold days, you could have some sort of gas backup. Next slide, please. This is just a quick shot of the roof showing how successfully we were able to manage everything. What you'll see here is some of the amenity space, some of the green space that's included as part of that amenity for the tenants. Over on the left, you'll see the solar panels that are above some of the bulkhead space, which provides some offset for the energy usage in the building. And what's conspicuously absent, or maybe you can see a part of it over to the right, is the mechanical equipment, which was successfully hidden away from view for many of the tenants, and we were able to keep that footprint relatively small. Next slide, please. In terms of the performance of the building, it's performing, these are modeled results. This is what we're anticipating it to look like once the tenants have all moved in and filled up. The EUI, as Alper mentioned, is energy use intensity. For a typical existing office building in our climate, we would anticipate that EUI would be about 89 or 90. That's using the AIA 2030 baseline. we're about 50% less in terms of energy usage than that. Where UI is coming in about 44, which is a bit better than the LEED baseline and the code target that we have. The Seattle Energy Code is relatively aggressive compared to a lot of energy codes throughout the country, so we had to meet that and exceed it a bit as well, which we were successful with. Next slide. And then finally, I'll just mention with, in terms of carbon emissions reductions, this is looking at the 20-year operational carbon profile of the building compared to an existing building that has gas boiler heating. The red in this chart is emissions associated with burning natural gas on site, and then the blue is the emissions associated with the electricity usage. You can see that the chart's dominated by the red, the gas usage on site, because we eliminated it from space heating and domestic hot water heating. What's left is basically the gas use associated with the cooking in restaurants on the basement level. And then the blue, we are lucky in Seattle in that our existing electrical infrastructure is mainly based on hydropower. So we have a relatively clean electric grid, clean amount of electricity to begin with. So it does mean that our emissions profile, that what we burn on site has an outsized impact. And, you know, as my last point, I will just say that, you know, a lot of you around the country may have a different profile to the way that your emissions between electricity and natural gas looks, but this is likely the direction that we're headed in as the grid gets cleaner, as more utilities bring more renewables online. The decisions we make with what we burn on site starts to have a greater outsized impact. So with that, I will turn it over to Stet to present the next case study.
Great, thanks, Dan. So I'm going to be talking about the electrification retrofit with heat pumps for a registered historic landmark, and similar to Alper's example, a challenging building. So this particular building, if you want to go to the next slide, is a religious facility in the city of San Francisco, and it includes two major components. So it is a sanctuary. The core of the building is an 1800 sanctuary. So to Dan's earlier point about let's focus on the envelope, this couldn't be a worse envelope. There were no air barriers in the 1850s, let alone insulation. And so there is this historic portion of the building which actually made it through the 1906 earthquake in San Francisco and the big fire. So it's definitely a prominent building. And then in the 1960s, also very similar to Alper's example, is they had a brutalist modern expansion, which pretty much quadrupled the size of the facility, where they added offices, administrative services, as well as a year-round school. And then this site also provides for seasonal homeless shelter, as well as commercial kitchen facilities. I will say that this particular client, who I've been lucky enough to work with for almost 15 years, has been going through continuous greenhouse gas emissions strategies and implementations over the course of the last 20 years. The biggest of which was the installation of a solar PV system on their roof in, I want to say it was around 2012 or so, to offset as much of their electrical load as they could fit. One of the key challenges with this building, which is similar to one Dan mentioned, is that as a registered historic landmark, we couldn't have any equipment be visible from the street, and we weren't allowed to essentially touch the aesthetic bounds, if you will, of the building. The existing building, which is not too dissimilar from a lot of projects that you're probably seeing, currently runs on a natural gas boiler. This one is naturally aspirated, and it has a supply water temperature through the building of 180 degrees. Which is, for the Bay Area, for California, is unnecessarily high, but that's what the building was designed around. And then one key element that will go into whether we have an impact on electrical service is that this particular building does not have air conditioning. And so the electrical service of the building is not sized to pick up any cooling load, even though there definitely is a cooling load now as San Francisco begins to warm up. Next slide. So as we approach a project, especially retrofits with heat pumps, there's kind of like this dream list that we'd like to go through that really involves understanding sort of in a deep way the energy use and hourly demands for the building, and then going through a whole series of sort of recommendations around efficiency measures before we get into the equipment selection. As Dan mentioned, our dream is to get the loads under control before we move into an area where we're trying to pick equipment, because as a number of the questions in the comment on Slido are bringing up, if we just try to do a hot swap of a boiler straight to a heat pump, you're likely going to run into some cost barriers. And so one of the key things that we can do for both life cycle improvement as well as greenhouse gas emissions reductions is try to right size that equipment, but first focusing on efficiency measures. So if you go to the next slide, for this particular building, we had already gone through, back one, sorry. We had already gone through a series of audits with this project. They've already done some air sealing work, some selective insulation improvements. They'd done a controls upgrade. They'd already kind of gone through sort of the low hanging fruit. And now they're really ready to do sort of the main equipment replacement. And so for our project, we really focus on a data collection portion, a cold weather stress test, which I'll talk about in a second, and then looking at load shifting, in some cases heat recovery, but especially in a load shifting scenario to try to minimize the heat pump size. And then we can focus on the actual piece of equipment. Next slide. So as I mentioned, and actually one of the questions in the Slido brought this up as well, the supply water temperature that we send from a heat pump, if it's an air to water heat pump, is really, really critical in helping us select equipment that's not only efficient, but works in our climate zone. So as I mentioned, this building has typically been served by 180-degree supply water temperature, which is excessively high for the Bay Area. So the first step that we actually went through on this project is we took an entire heating season, and every 2 weeks we reduced the supply water temperature. We call this sort of a wintertime thermal stress test. You can call it a sort of wintertime supply water reset test. The idea is essentially to run a limbo on your building's heating hot water temperature. How low can you go and still meet your heating demand? And the key is to let everybody know this is happening and make sure that people have an opportunity to raise a flag if there are spaces that they're working in or certain other areas in the building aren't able to meet comfort levels. We also trended the thermostats and tracked them to check at what point temperatures weren't able to be met. And then we made sure that that winter season was sufficiently deep enough that it represented sort of what we would call a typical winter. So the further to the right that you can go, the lower that water temperature you can go, you're going to have more options for which heat pumps, which manufacturers you can work with. More and more heat pumps are serving higher temperatures, but the bulk of them are better to serve at low water temperatures. And so in this case, we are able to go from 180 degrees down to 150 with no problem. And we're going to probably be spending this year doing another test to see if we can go even further down. Next slide. So buckle up. I'm going to walk you through a whole bunch of graphs. They're not meant to be painful, but I want to walk you through sort of the process that we use to right size equipment and try to reduce our electrical loads. So these are actual measured electrical loads from that building for an entire year. And you're going to see this chart format sort of show up a couple times. It's from the morning is at the bottom, evening is at the top, and from left to right, it's January to December. That big blue swatch in the middle is actually where this particular project, where they export energy to the grid. So those are all hours where they're producing more power on site than they consume from their PV system. Next slide. We also took a year-long worth of data and actually measured the energy use coming off of their boiler. So this is a true profile for this building. It's not modeled data. This was actually coming off of measured data. You can see that 5:30 a.m. they kick on their boilers through the whole winter season. They do their morning warm-up. And you can see in the summertime, the boiler is completely shut off for this particular site. Next slide. One of the questions that comes up a lot is, how do heat pumps perform in cold weather or cooler weather? How does that impact performance? So one of the key things that we're doing when we do one of these analyses is actually looking at a temperature profile for a site. We can use either typical meteorological files, or more recently, we're also looking at sort of extreme years where we've seen extreme lows or extreme highs. In the next slide, you'll see how that starts to play out with performance of equipment. So most folks know that air source heat pumps, their performance curve, or how efficient they are, is dependent on two things: the supply water temperature that we're sending out, which is what I talked about earlier, and also the air source, or the temperature of the air that's coming into the unit from the ambient air. So most manufacturers, you can extract this curve from them. It's often painful, but it's doable. You can get this performance curve, and we can map that over outside air temperatures and then use that relative to our actual weather file. And the graph on the right is what we produce to sort of look at what is the effective heat pump COP given our current weather conditions. And so you can see it varies widely. And this is for the Bay Area, which is considered a relatively mild climate. But the COP that we would expect for this building delivering between 150 and 160 degree water from an R513 refrigerant ranges all the way from 2.4 up to almost 3.5. So we see a pretty big variety. In a colder climate, you could expect this to actually get down into the 1.5, 1.6 range for COP. Next slide. So all of that combined, our weather file, our true load profile, we can actually fold that into a performance curve of where we think that the heat pump is actually going to provide energy for our site. So this is our prediction of the heat pump sizing, or sort of the demand on the electrical side for the project. Next slide. So we'll fold that then and our actual greenhouse gas marginal short-term emissions rates for our grid. And similar to Seattle, California has a really favorable grid for electrification. So for us, there's less drive to focus on COP to make sure that our greenhouse gas emissions are reduced. But as you look in, say, the middle of the country, in sort of the Chicago region or Indiana, states like that, the grid is about twice as dirty on an annual basis. And so their COP is going to matter even more, focusing on those low supply water temperatures so that your COP, or the efficiency of the heat pumps, can go up as high as possible. On the next slide, you can we'll show our hourly emissions profile. So again, this is the boiler burning on site. We can convert the usage of the boiler to an emissions profile. And the key is we're trying to drive down the overall emissions for our project. So on the next slide, you can see what happens when we take that COP of the heat pump. We apply that short-term marginal emissions rates for each hour, and for our site, where we know that we're actually overproducing power from our own PV system. And we can actually now look at the delta, the difference between the emissions before on the boiler and what they were coming from the heat pump. I want to point out, though, that those January hours, sort of January, February, 6 a.m., it's cold outside, it's our winter time, it's also early in the day, and we're asking the heat pumps to do the most amount of work right at that time. So as a design engineer, that's where I begin to focus. If I'm truly trying to reduce emissions and right size a heat pump, those short-term bursts of energy, I don't necessarily want to pick a heat pump or size a heat pump just for that load. On the next slide. This is just the conversion, comparing each of those emissions profiles next to each other. And you can see that the overall greenhouse gas emissions for this particular project, we saved about 31% just by doing the conversion from a boiler to a heat pump. Now, those savings are going to vary across the country. We just finished an analysis similar to this in Chicago, where we were seeing about annually a 5% savings on today's grid, but projecting out in the future more significant savings going forward. Next slide. Some of the key challenges around electrification retrofits, especially around historic buildings, is just finding space for the equipment. So here we used modular heat pumps, similar to the other projects, so that we could do a sort of a custom fit. These ended up located on the roof away from all the sight lines. But I did want to highlight, because this building did not have air conditioning, the electrical service was way undersized to meet this new heat pump load requirement. So we did end up having to upgrade the service, and we couldn't do it lightly because the actual existing service for this building was original to the 1960s expansion. And so nobody was willing to touch it. So it is going to be getting a full upgrade. Next slide. One of the key things, I think, from an implementation standpoint that I just want to highlight that's really important is that those key hours in the morning, for us, we are able to actually downsize the heat pump just by adding a thermal energy storage tank. So we added, I think, around 2,000 gallons of storage for this particular project to get through those first 3 hours, in combination with changing the morning warm-up start point. So we could actually save a significant amount of costs because, as you can see, of course, across the rest of the year, the peak load is not that high. So sizing on a peak occurrence that's very short in duration is not what we want to do for a cost-effective design. So I encourage everybody to think about thermal energy storage or targeting appropriate warm-up start times to right-size your heat pump applications. Next. So the second project, and I'll go a little bit quicker, and kudos to everybody who lasted through all those graphs. But for the next project, I want to talk about a net zero energy retrofit, or actually net positive energy retrofit to an existing building. And this is the DPR construction headquarters in Sacramento. Next. Just really quickly, the before building and after. So not only was this a retrofit, but this was also an expansion. We added about a third of the building size was actually added as part of the retrofit. So it was expanded as well as electrified and taken to net positive energy. The measured EUI of this project over the last year has been an EUI of 14, which is really phenomenal for the Central Valley of California, which gets both exceptionally hot as well as quite cold. Next slide. Just some floor plans so you can get a sense. There's a ground floor tenant space, and the addition is shown on the right of going up and out for the project. So square footage increased as well as decarbonizing the existing systems. Next slide. One of the key things that was done for this project, both to be sort of climate smart, but also to improve indoor air quality and wellness, was this building is considered mixed mode. So we have both operable windows, operable skylights, as well as a VRF system with DOAS. So when the weather is beneficial, the building can close down and be airtight. And then the DOAS system can provide ventilation with VRF, providing the heating and cooling. But for large portions of the shoulder seasons, we don't have a significant humidity load in the Central Valley in California for some of the shoulder months. And so we're able to naturally ventilate the space. And that's one of the key things that led to the low, ultra low EUI. One thing I do want to point out is that all of the steps that lead to a heat pump, oh, you can go on, that's fine, that go into a heat pump retrofit, it's really about reducing loads. So in this case, lighting loads were reduced by doing extensive skylighting with solar tubes. So a very low thermal impact, but really big impact of reducing the electrical lighting demand during the daytime hours. So you can sort of see a before on the left and after on the right. Much better daylight condition in the right, and in person it actually looks even better than the construction photos. Next slide. The most exciting thing though on this project, and again, it's all about trying to reduce the size of that peak load. We size systems based on peak. On the last project, I talked about using thermal energy storage to reduce that peak or draw it out so we can right size a heat pump. In this particular project, that peak load was actually a summertime load. In Sacramento, actually just a few weeks ago, we saw temperatures of 112 degrees. That's a pretty excessive temperature. And in the wintertime, we also see temperatures below freezing. This existing building actually had a whole underground concrete sort of bunker that we couldn't use in the retrofit to be inhabited. And so we actually turned it into a thermal labyrinth that we bring the outside air in. It travels through this concrete underground bunker, and we use it essentially as a tempering device. And so we were able to see significant temperature peak reductions, both in the wintertime. That thermal labyrinth actually warmed up the air by the time it gets to the heat pump or the VRF head units. And in the summertime, we were able to reduce that summer peak as well. And so that thermal labyrinth or preheating, pre-cooling strategy was a really effective way for us to downsize the size of the heat pump, reduce the impact on the electrical service, et cetera. Similar strategies can be deployed through heat recovery ventilators. If you have a building that has a very high air change exchange rate, you should definitely be focusing on heat recovery first as a tempering device for all those loads. So again, we can reduce the size and sort of the peak sizing of equipment, because that's going to drive your system costs across the project. Next slide. Here you can just see sort of that new addition. So everything below the slab was existing building. We cut through the roof slab and actually added the second story was done in cross-laminated timber, similar to both Dan and Alper's examples of trying to minimize the embodied carbon that's being thrown into the project, take advantage of what's already there. You can see the ductwork from the DOAS system, etc. On the next slide, though, I do want to highlight one of the other key things that allowed us to right-size the heat pump and reduce its overall size. The first one was we added ceiling fans, and that increased air movement across the skin of the body, especially in wintertime, allows us to set the cooling set point up about 3 degrees. So for this project, the cooling set point is actually 78 degrees instead of like a typical office building of 75, because that additional air movement provides that sense of comfort. That change in, or adding ceiling fans plus the change in the set point allowed us to actually reduce the size of the heat pump as well to meet that peak summertime cooling load. So I think that's my last slide, and I am handing it. Oh wait, I have one more, just showing that the building has trended for net positive energy over the last year and a half or so that it's been fully operational. And then it did really well during COVID, but we kind of discount those years. But now I'll hand it back to Nora to jump into the Q&A.
Great, thank you, Stet. So you can see the slide here is showing a reminder of all the case studies that were just presented. And now I'm going to go over to Slido and pick out some questions to ask our presenters. So the top question right now is, what is heat pump efficiency / COP for heating in colder climates? How does the cost of heat pump compare to a gas equipment when delivering the same amount of heat in colder ambient conditions? So I know Alper spoke a little bit about this in the very first case study, saying that that system was 20% more expensive than a traditional system. So maybe I'll move over to Dan to see if you have anything to add about COP in colder climates or cost for your project.
Yeah, in general, as the temperature goes down, the COP of the heat pump also goes down. However, modern heat pumps can go to lower temperatures than the heat pumps you might have seen. You know, I've talked to some people who installed them 10 years ago, and they say it didn't work in cold temperatures. The technology has definitely improved and made big steps. You can get ones that are rated down to like -4 degrees easily. The newer technology that I'm interested in too is using CO2 as a refrigerant, which actually allows for much lower, colder temperatures too. That is only just starting to come on the market, so it's still in its early stages, but that is coming. Just in terms of cost, it is going to cost more than a gas boiler on a 1-for-1 basis. But if you look at your full emissions, how you're accounting for emissions on a building level, it can start to make more economic sense when you look at the other sorts of upgrades you may have to do to also get your emissions down by the same level.
Thanks, Dan. Stet, do you have anything to add?
No, I mean, I think Dan nailed it. There is a lot of technology that is increasing the performance for cold climate heat pumps. Some of the things you can start to look for are inverter controls on the compressors, enhanced vapor injection on the refrigeration circuit. That allows the coil temperature that's outside to go far lower, and you get a better delta T relative to outside air temperature. And so that's going to drive up both capacity as well as your coefficient of performance. So I'd say that's the area in the market where manufacturers are putting the most attention right now is in cold weather performance. And so each year we're seeing more and more products that can make higher temperature water and work at lower ambient air temperatures. I would highlight, though, that your existing building still has a lot of places that you can still heat from that can improve performance. And one of my favorite, if you're in the multifamily world, is looking at your wastewater heat pump or heat recovery heat pumps off of your wastewater stream, because that's a really high quality source of heat. And so you can get a very small heat pump relative to an air source heat pump because it's stealing heat out of 75-degree effluent as opposed to pulling heat out of 0-degree air. And so you can buy a smaller heat pump, still make a ton of hot water for your building, and get exceptional greenhouse gas reductions. So it's about matching the right technology, I'd say, to the application and the climate zone that you're in.
Thanks, Stet. I like that. Steal the heat from somewhere else. That's a good, good theory to live by. So the next question that I'll jump to is directed towards Alper. So did you have to deal with upgrades to electrical service infrastructure to incorporate the electric heat pumps?
Yeah, so for this building, the electrical structure had to be upgraded, not necessarily because it's being converted to electrical, but the program was changing into a lab program, as you can imagine. Like the overall the electrical capacity actually tripled. But that's again because of the lab equipment. In terms of the conversion to electrification for the building plant, I mean, there was a water cooled chiller there, so air source heat pumps. Replacing that equipment with air source heat pumps doesn't make a huge difference. Again, this is for a cooling dominated building in a temperate climate. So yeah, if you are looking at a colder climate, you may have to add like electric resistance backup for heating. So yeah, that's definitely something to consider for other projects and other locations.
Thanks, Alper. Dan, would you like to speak to that same question on the project you spoke about?
Sure, yeah. I mean, with our project, it was a historic building, so we did have to upgrade the electric capacity. It was already, because we were doing substantial renovation anyway, it was already slated to be on the installation anyway. So that just be going to all electric meant we just had to look at additional capacity. The one other thing I'll mention too is it didn't happen with this project, but projects where you may have like underground parking or parking adjacent, where you're also looking at adding potential EV charging. Looking at increasing the electrical capacity at the same time for all of these sorts of electrification initiatives, trying to focus it and do it once and add enough capacity for all that stuff is probably the best way to go, instead of realizing that you need more down the line later.
Right, that makes a lot of sense. And on that note, Stet, you talked a lot about the electrical service upgrade in the historic landmark. Someone asked specifically if you know how that affected the cost of the project.
Oh, that's interesting. So so it obviously was it was actually, that cost was more than the heat pump cost, like without a doubt, for this particular project, because we also had to bring a different phase of power to the building. But I would say that for that building, because the original electrical service was still the original 1960s service, they were actually running into a problem already of finding anybody who could touch it, maintain it, or do any service work to it. So it was at end of life. To replace it in kind would have triggered a whole bunch of code violations for them, because they actually didn't have enough front space clearance for their, they only had about 18 inches in front of the panel. So there were a whole bunch of other reasons why that service needed to get replaced, as well as to service a new elevator. There were a bunch of things. And so they wanted to just pair it and make sure that the new service that they were going to get was going to be right sized both for today and the future. So it was mostly aligned with a pretty big capital investment they were going to need to do either way.
Okay, thanks, Ted. That makes sense. It kind of goes with what Dan said, trying to future-proof the electrical service of the building. If you're going and doing all of that work, you want to do it at one time. So something that I think was already touched on in a lot of the projects, but I'll just ask each of you to speak to it, is, are there concerns about peak load for any of these locations? So I'll start with Alper.
Concerns about peak loads for any of these locations? You mean like I'm guessing that's the question is having an electric system. For the cooling side, we don't have any, concerns. It's, the air source heat pumps operate very similar to air-cooled chillers. They can provide like really low temperature chill waters, down to 44 degrees, no problem there. Heating, as Stet already talked about, you can't go above like 110 in general, or not advised to do so. So yeah, like for our location, we didn't have any issues because the outdoor temperature doesn't go that cold in the Bay Area. Yeah, if you were in colder climates, usually what we are doing in projects in other climates with electric central plants is either keeping the existing boilers as backup for backup use, or suggesting some sort of electric resistance type of backup heating, or geo is another option, geo loops for wintertime as backup, or thermal storage.
Thanks, Alper. So I actually misspoke. I will not be jumping to everyone because we have 1 minute left. So with that, I'll close out the question portion of the webinar and we can jump to the next slide. And thanks to the speakers for answering questions. So this side here, we just have kind of a plug for the Better Climate Challenge. Like I said, everyone on this call is on that project. We have our technical account managers that were speaking, and I also support the Better Climate Challenge. And so this is going on right now. The goal of the Better Climate Challenge is portfolio-wide reduction in greenhouse gas emissions of at least 50% within 10 years. So you can go to that link below if you're interested in joining, or talk to your account manager. Next slide, please. So here, I just wanted to highlight the Better Buildings webinar series. There's a lot coming up and a lot of things going on around decarbonization. So take a look at the things that are coming up in the near future and sign up for more webinars. Next slide. And here, I just wanted to highlight the dates of the Better Buildings Summit for next year. That has been scheduled for April 11th through 13th, 2023. We hope to see you there. Next slide. And thank you. We really thank you guys for joining this webinar. We had lots of attendees, so many great questions we didn't get to, but we appreciate your support and interaction. Hope everybody has a great day.